All right, so we are going to go with section 1.2, which is the only section out of this book in chapter 1 that we will be doing. We'll move into chapter 3, so this section will be included in our chapter 3 test when we get to it. But as you can see, we're going to look at some estimation, graphs, and some mathematical models in this section. So here we go. Here's what we're going to be looking at. We want to use estimation techniques to arrive at an approximate answer to a problem. Apply estimation techniques to information given by graphs, and develop mathematical models that estimate relationships between variables. That's something else we'll hit on later in the year when we talk about lines. But if you notice, some estimation is the big topic for today. So, what is estimation? It is the process of arriving at an approximate answer to a question. Methods that we do estimate. Rounding numbers is a big way to do estimation. We can use graphs. A lot of graphs you have to get an estimate on. You can't get exact by looking at it because of the way it's set up. And we can estimate using mathematical models, like what will happen in the future based on what has happened in the past. That's sort of how we would use mathematical models. Next slide. All right, so rounding whole numbers. So we have a little bit of trouble from this from time to time because we haven't done it a whole lot lately. But when we are rounding whole numbers or rounding numbers, you look at the digit to the right of the digit where rounding is to occur. Okay, if the digit to the right is 5 or greater, you add 1 to the digit to be rounded and replace all the digits or the numbers to the right of that with zeros. If the digit to the right is less than 5, you do not change the digit and you replace all the digits to the right with zeros. So if we had the number 237 and we wanted to round to what is the tens, since I'm rounding this number, I'll look to this number here. If it is 5 or greater, add 1 to the digit we're rounding. We're rounding the digit 3. So that is greater than 5. So I would add 1 to that digit, make it a 4. And then anything else to the right of that adds to a 0. Same thing if it were a decimal, such as this, 3.235. If I'm rounding to the 10th place or that 2, I'll look to the number to the next to it. It is less than 5. So this number actually stays the same, the number I'm rounding. And then everything after that turns to a 0. Now, when we are writing a decimal, these right here are called trailing zeros. And we don't have to put trailing zeros on a number that is a decimal. So we would probably put 3.2. Okay. In our MATLAB program, rounding is very important. You have to really pay attention to where they ask you to round things. Because if you round it a little bit wrong, even though you know the right answer, you're going to miss it. And if you'll notice here, whenever you see this, that means something is estimated or is approximately equal to, something's been rounded or something like that. All right, so let's go here. All right, so let's look at this example. Rounding a whole number. All right, round the world population. All right, what's this number? Here's our ones, tens, hundreds, thousand, 10,000, 100,000, million, 10 million, 100 million, billion. This is 7,058,746,857 is this number. So if we want to round it to the nearest 100 million, we go to the 100 million spot, which is right here. Right? So that's the number we're rounding. So we look to the number to the right of that, 5 or larger. Yes, that means this number we add 1 to, and everything else goes to a 0. So this is where they get 7,100,000,000 right here. All right. If I want to go to the nearest million, well, here's the million spot right here. Look to that. What is that? That is larger than 5. That's 5 or larger. So once again, I add 1 to this. The rest of these go to 0. So that's why this 8 goes to a 9 there. The rest are zeros. So rounded to the nearest million is 7,059,000,000. Okay. All right. With a decimal. Okay. Pi is one of these, right? One of these numbers that has a decimal that goes on forever. So anytime you're using pi as a number, it's an estimation. You always have to estimate it because this decimal goes on forever. And we can't write down numbers that go on forever. So anything we write down as a number for pi is an estimation. If we ever want to put down exactly what pi is, you have to actually use the symbol. So here they want us to round. This is pi 3.141592, so that's out to 6 decimals. They want us to round to the nearest hundredth. Remember, whenever we have the th on the end of them, that is a decimal. So remember how our decimals start. It goes tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, so on and so forth. So to the nearest hundredth, tens, hundreds right here. So we're looking at this right here. That's what we're rounding to. So now we have to look to the number to the right of it, which is 1 less than 5. So this number stays the same. Everything else goes to 0, which trailing zeros we can drop off. And this is where they've rounded to 3.14. So that's pi to the nearest hundredth. The nearest thousandth, well, here's our thousandth number. We look to the right. That is 5 or larger. So that means we've got to add 1 to this digit. Everything else goes to a 0. So that's where they get this 2 right here. 3.142, we drop our trailing zeros. Nothing too difficult there. All right, let's see what we have next. All right, now this is just an example where there's suppose you're going to the store, have in your mind about what you want to spend, and as you're shopping, you're just sort of rounding things off and adding them up in your head. You're just they're wanting to round it to the nearest dollar. It says you purchase bread for $2.59, detergent $2.17, a sandwich for $3.65, an apple for 47 cents, coffee $5.79 for a total bill of $18.67. Is this a reasonable amount? So what's the question? Is $18.67 reasonable for those? How can we figure that out? Well, they're just saying round to the nearest dollar. So 2.59, $2.59 is going to round up to 3. That 1 is less than 5. That's going to stay and round to 2. That 6 is bigger than 5, so that's going to round to 4. 47 cents is going to round down to 0. That's going to round up to 6. Okay, now it's easier in our head to add 3 plus 2 plus 4 plus 0 plus 6. 5, 6, 7, 8, 9, 15, $15. So estimating in my mind, I got $15. So is $18.67 reasonable? Well, they're saying that it seems a little bit high compared to the estimate. So you might want to double check your receipt or something like that. Obviously, if everything rounded down, then this is going to be a little bit low, but this rounded up, that rounded down, this rounded up, that rounded down, this rounded up. So 15 should be a pretty good estimate. All right, next problem. All right, so looking at a graph, this is a particular one here is a circle graph, right? However, little pieces of the pie that represent all part, right? The whole thing is always going to add up to 100%. So use a circle to represent the whole and divide it into sectors proportional to their part of the whole. So what we have here is, well, let's read over here. According to the U.S. Census Bureau, in 2012, there were 229,937,770 Americans 20 years and older. Assuming the circle graph is representative of this age group, we want to determine a calculation that shows the number of Americans 20 years and older who define old age by a decline in physical ability, and we want to use rounding to find a reasonable estimate. So as we look over here at the chart, whenever you have a chart or graph, it's always very important that we read around it and decide what it means. It says these are the Americans' definitions of old age. So they did a poll. What do you think considers somebody old, makes somebody old? Well, 32% of the respondents said a decline in mental functioning. That's how I can tell when somebody's getting old, is when their mental capacity starts going down. 14% said a specific age, whatever age you think is old, 65, 60, 24, I don't know. All right, 1% of the people said, I don't know what makes somebody old, which is probably the most honest people there. 9% said when they retire, that's what makes somebody old. Of course, you look at a lot of professional athletes and things like that, they retire in their 30s. So I don't know how good that is. Becoming a grandparent, 3% says that's what makes somebody old, when they become a grandparent. Decline in physical ability. Now, that's the biggest one. That's what most people decided, is when they decline in physical ability is when you start getting old. Anyway, what's the question? We want to know the number of Americans 20 years and older who define old age by decline in physical ability. So this is it right here. So they're wanting us to use rounding to find a reasonable estimate. Well, first thing I'm going to estimate is right here. This is how many total Americans there are. I'm not going to use that number. What number is very close to that? Well, right here, 229 million. Wouldn't you say that that is very close to 230 million? So I'm going to use 230 million. And I need to find, that's 41%. I'm going to use 40% as an estimate. That's pretty close. That's pretty close. So if I take and multiply the percentage, 40% times that, that's probably going to give me a good estimate on how many people think that a decline in physical ability is what makes somebody old, right? So you have a calculator. All right, I multiply this by 0.4. I'm going to do it on my calculator real quick. So 230 million times 40%, which you would put in as 0.40, or on your calculator, you can put 40%. And that is about 92 million. So I'm multiplying that by 0.40. So about 92 million Americans 20 years and older said decline in physical ability is what makes somebody old. Okay, all this information is not important. What's important is we were able to estimate this number here, estimate this number, multiply them, and without anything very difficult to do, find an estimation. That's the whole idea behind estimation, looking at this circle graph. So let's go on to our next. Now, this is just their explanation. This is gone through exactly what we just talked about. 40%, 230 million. They got 92 million. All right. So bar graphs, different kind of graph. Bar graphs use vertical or horizontal bars to represent each item. The length of the bar determines the amount, and we can use bar graphs to make predictions. So let's see how this is going to work. All right, so here is this bar graph. Life expectancy in the United States by year of birth. So in 1950, females' life expectancy was 71.1 years, males 65.6. Down here, 2010, closer to our time now, about 10 years ago, it had gone up. Males had gone up by 76.2, and female life expectancy at about 81.1 years. All right. So, wants us to estimate a man's increased life expectancy, round to the nearest hundredth of a year for each future birth year. All right, so basically what they want to know is how much, and they said what, the man. So we're looking at the males, the red ones. So on these red ones, it's wanting to know about how much is that going up per year. Well, the easiest way to figure out how much is going up per year is to find the total difference between the ending and the start, which is what they did right here, and divide that by how many years it took to get there. 1950 to 2010. So they're going to subtract 210 minus 1950. That's 60 years. So 76.2 minus 65.6, which is 76.2 minus 65.6 is 10.6. We're going to divide that by 60, and you can see right there, 0.18. Now, what does that 0.18 mean? All right. Well, it means life expectancy per year, right? So each year, the male's life expectancy is going up by 0.18 years. All right. So this is what's going to allow us to make a prediction. If I know it's going up 0.18 years and I want to know what is going on in the year 2020, this year, what is the male's life expectancy based on this graph? Notice the male's is going up. Where's it at right here? Okay. Well, that's going to be 10 years past this last one. So what I can do is I can say, okay, if it's going 0.18 every year, 0.18 times 10 is 1.8. So that means in 220, it's going to be 1.8 years more than this year right here, which was 10 years before, which was at 76.2. So all I've got to do is take 76.2 and add 1.8. And it's telling us that a male's life expectancy this year in 2020 should be 78 years old. So that's how we can use estimation to make a prediction. See what the pattern is and continue out the pattern. All right. And this is just walking you through that right there. Notice they did it a little bit different. They multiplied it by 70. Well, where did they get this 70 from? Look what they started with, 65.6, which was in 1950. All right. If you add 70 years to that from 1950 plus 70, where are we at 2020? So what they did is they multiplied by 1.8 times 70 so that they could find out, okay, 70 years after this, where is it at? Going up by 0.18 per year. Notice for 70 years, it increased by 12.6. They added that to the 65.6, and they got 78.2. All right, whereas we got 78. But we used a different estimation. We went from right here and added 10 years to it. Okay, so this is an estimation on a bar graph, so answers could vary slightly based on, in this case, where we started from. Okay, my mind took me 10 years past this. They went, okay, 70 years past this. Either way, we're getting right around 78, 78.2, 78.1 years old is the life expectancy in 2020 for a male. All right, line graphs. All right. Here's a graph of a woman's average age of first marriage. All right. Line graphs illustrate trends over time. In this case, the horizontal axis right down here represents time. The vertical axis represents the amounts, in this case, the age. You'll notice in 1890, female would get married for the first time at the age of about 22. Notice back in the 1960s and 1950s, it dropped down to just over 20 years old, right there, 20, between 20 and 21. 2010, it has moved up to 26 years old. So obviously the trend is saying that women are waiting longer to get married. Now, what do you think that could be? What are some reasons that could be? I would say there's a lot more women going to college now, so they're waiting until they get out of college. There are also a lot more women in the workforce. So they're going to college, getting a job before they decide to get married. There's probably more women not getting married. All of that's causing the age to go up. All right. Back in the 60s and 50s, that's where a lot of women stayed home, got married at an early age, and were housewives. That's no longer the case. That's my theory. You may have a different theory. Let's see what they're going to ask us to do here. Oh, different chart. Okay, so same thing. We're using a line graph. Find an estimate for the percentage of seniors who smoked cigarettes in 1995. So we're talking about high school seniors. So we're talking about people your age. If we look at the chart, year across the bottom, the percentage of high school seniors that smoked cigarettes. So this was probably come out before vaping became popular. So we're not talking about vaping at all. These are actually smoking cigarettes. If you'll notice, back in 1980, it was right at 30%, and it stayed pretty level for the next 10 years till 1990. And then from 90 to 95, it looks like it actually went up. And then what started happening after 1995? Started going down, down. In 2010 was its lowest point in 30 years, about 20%. So this trend is telling us that seniors in high school, fewer and fewer are smoking cigarettes. So here it says 1995, 34% seniors smoked cigarettes at the high point. Okay, let's see if they're going to ask us. Yep, here's a question. In which 5-year period did the percentage of seniors who smoked cigarettes decrease at the greatest rate? So we need to understand the question. Which 5-year period, if you notice, these are all 5-year periods, and we want to know decrease. So decrease, is that going to be a line going up, or is that going to be a line going down? It's going to be a line going down is a decrease. And the greatest rate, and we'll talk about rates a lot more when we get to slope later on in the year. So basically, which one is decreasing at the greatest slope? Well, right here. That looks like to me the one that is most downhill. This here is pretty close, but I'd say it's this one right here. And so I'm going to say the years 2000 to 2005 was the greatest rate that smoking decreased in high school seniors. And that's what they said. When was the greatest increase? And really the only increase was right here, right? From 90 to 95. That's the years I graduated high school and started going to college. That's when more people started smoking for whatever reason. Not me, but others. Anyway, that's reading the line graph. Let us move on. Here's another one. Alcohol use by high school seniors. In which year labeled on the horizontal axis did 50% of seniors use alcohol? So this is saying 1980. It was at just above 70% use. 2010, it had dropped down to about 40% of high school seniors using alcohol. And the question just is 50%. So what we want to do is look at 50% and just want to carry 50% across until we intersect the line, which was right here. Then we drop down, and there it is, in the year 2000. So probably, I don't know, most of y'all, a little bit before most of y'all were born. So there's that, just another example of reading a line graph. All right, here's something else that may be of interest to you. The cost of attending a public college. This is probably four-year schools, not junior colleges. Of course, you all could go to junior colleges for free now, but this is probably four-year colleges. And this is the average cost of tuition and fees in public four-year colleges. That's what it is, four-year colleges in years. So if you'll notice, as this goes, it is increasing pretty quickly. Every year, that is costing more and more and more to go to college. And there doesn't look to be any end in sight. So once again, we're going to estimate the yearly increase. So this is what we did earlier. If we want to find out what is the average increase, well, we go with where we started and take where we end, and we subtract those two numbers. So 7,020 minus 3,362 is 3,658. So from this 2000 to 2010, it increased by $3,658. How many years is that? Well, it's from 2000 to 2010, so that's 10 years. So 3,658 divided by 10, we would just move that decimal over one spot, is 365.8, so about $366. So every year, the cost of college tuition and fees is going up by about $366. So this is another case where we could predict where is it at about right now in 2020. Well, it would be about $366 more than that one right there, right? If the trend continued. And they're actually creating a formula here. And notice how this formula works. X is the years. So what they do is they start with the low. This, whenever you create an equation, this is what you do. You always start with the first amount, which was 3,362. And each year I'm adding $366. So I'm letting X represent the year. So if I've added it for 2 years, that would be 2. If I'd added it for 8 years, that would be 8. So I just simply multiply the number of years past 2000 times 366, add it to this number right there, and that's going to tell me about where I'm at. So this is just another way to predict. Now we could predict, if we want to know 50 years from now, we could just put 50 in for X, and that would give us a prediction. The equation helps us predict out longer times further on down the road. All right. Looks like that may be it. Yep, I believe that's it. So what we are going to do is I will open up 1.2 as your first assignment. And you'll log on to MyPearson and get started on 1.2. And that is it. The end.